They become tight and powerful when it's extended. When the radial extensors or the ulnar extensor contract separately, they help to produce radial or ulnar abduction of the wrist. They do this in conjunction with the corresponding wrist flexor muscle, either radial or ulnar. It's good to study muscles function by function, as we've done so far in this section, but it's also important to see how they all overlap and fit together. If you'd like to use this next overview as a review section, turn off the sound. Let's look at a dissection that includes all the muscles that we've looked at so far in the arm and forearm and in the adjoining shoulder region. Here's the biceps with its two heads hidden both by the deltoid and pectoralis major. Here's the short head of biceps running close to coracobrachialis. Running up behind biceps and coracobrachialis is latissimus dorsi. Here's brachialis going to its insertion on the ulna, and here's biceps on its way to the radius. Here's pronator teres crossing over from the medial epicondylar ridge to the radius. Also arising from the medial epicondyle, here are flexor carpi radialis, palmaris longus, and flexor carpi ulnaris. Here's pronator quadratus, deep to everything. Now let's go round and take a look at the back. Here's the triceps with its long head going up beneath the deltoid. Here's teres major, and here's latissimus dorsi again. Here's triceps going to its insertion on the olecranon. Here's brachioradialis going to the radius here. Here's extensor carpi radialis longus and brevis, and extensor carpi ulnaris. Lying deep to all the muscles which share the common extensor tendon is supinator, all on its own. At this point, our picture of the forearm is complete as to some functions, incomplete as to others. That's the way we're going to leave it for now. We'll be returning to the forearm in the next section to look at the important muscles there that we've not seen yet, the long muscles of the fingers and of the thumb. Now, let's move on to look at the vessels and nerves of the region. We'll go from the shoulder to just below the elbow. First, we'll look at the veins. Many superficial veins from the forearm converge just below the elbow to form two large veins, the basilic and the cephalic. The cephalic vein stays at a superficial level as it runs up the arm over the biceps. At the top of the arm, it lies between the deltoid and pectoralis major. The large vein crossing the front of the elbow is the antecubital vein. It crosses from the cephalic to the basilic vein. The basilic vein then runs up the medial aspect of the arm to join this brachial vein, which is one of a pair. The two brachial veins join together as they pass up the arm. Here they are joining to become one brachial vein. The name of this vein then changes. Up here, it becomes the axillary vein. To get a good look at it proximally, we'll remove pectoralis major. Here's the axillary vein, running alongside the median nerve and the axillary artery, and disappearing with them behind pectoralis minor. Now, let's look at the artery and the principal nerves of the arm. From here on, the veins which run parallel to the arteries have been removed to simplify the picture. Here's the main artery, the axillary artery. It emerges from beneath pectoralis minor, surrounded by major nerves. As it passes into the arm, its name changes. From here on down, it's the brachial artery. Here, right next to the latissimus tendon, it gives off a large branch, the deep brachial or profunda brachii. which passes backward deep to the triceps. Along with it goes the radial nerve, which we'll see in a minute. The brachial artery runs down the medial side of the arm alongside the brachialis muscle. The median nerve crosses over the artery. The brachial artery passes beneath the bicipital aponeurosis, which we'll remove. Alongside the biceps tendon, the brachial artery divides into the two major arteries of the forearm, the radial and the ulnar. The radial artery stays quite superficial. It runs down the forearm between pronator teres and brachioradialis. The ulnar artery has a much deeper course. It dives down alongside the brachialis tendon and passes deep to pronator teres. We'll leave the arteries there. We'll see their further course in the next section. Now we'll go back up to the top and look at the nerves. 4 nerves surround the axillary artery as it emerges from beneath pectoralis minor. They're the musculocutaneous, the median, the ulnar, and the radial. We'll look at them in that order. Here's the musculocutaneous nerve. It supplies 3 flexor muscles in the arm, the first of which is a shoulder flexor, coracobrachialis. The musculocutaneous nerve runs right through coracobrachialis and emerges here, deep to the biceps. It runs down the arm between biceps and brachialis, supplying both muscles. It emerges here to become the lateral cutaneous nerve of the forearm. The median nerve and the ulnar nerve both run all the way down to the elbow without supplying anything. They start out close together. Halfway down the arm, they diverge. The median nerve stays close to the brachial artery, crossing in front of it. At the elbow, it lies medial to the artery. It dives down between the brachialis tendon and pronator teres and passes between the 2 heads of pronator teres to enter the forearm. The ulnar nerve slants backwards. It runs down just medial to the triceps tendon and behind the medial epicondyle. It turns a sharp corner round the underside of the medial epicondyle, where there's a fibrous tunnel for it. It passes between the 2 heads of flexor carpi ulnaris to enter the forearm. Once they get below the elbow, the median and ulnar nerves get busy. Between them, they supply all the flexor and pronator muscles of the forearm. Of the muscles that we've seen already, the median nerve supplies 4: pronator teres, flexor carpi radialis, palmaris longus, and pronator quadratus. The ulnar nerve supplies 1 muscle that we've seen so far, flexor carpi ulnaris. Lastly, let's look at the radial nerve. It has a long spiral course from here round to here. Up here, the radial nerve lies behind all the other nerves and vessels. Just below the latissimus tendon, it runs back between the long head and medial head of triceps. To follow its course, we need to go right round to the back and find the same spot again from behind. Here's the long head of triceps, here's the medial head, and here's the radial nerve. To see where it goes next, we'll remove the long head of triceps. As the radial nerve passes round the humerus, it lies right on the bone. It runs between the medial and lateral heads of triceps, then runs beneath the lateral head to emerge here, still right on the bone, just above brachioradialis. Under cover of brachioradialis, it reaches the lateral epicondyle, where it divides into a deep or motor branch and a superficial or sensory branch. That's as far as we'll follow the radial nerve for now. Of the muscles that we've seen, the radial nerve supplies the triceps, anconeus, brachioradialis, all 3 wrist extensors, and supinator. To end this section, let's briefly review first the vessels and then the nerves from the shoulder to the elbow. Here's the cephalic vein and the basilic vein, the antecubital vein, the brachial vein, and the axillary vein. Here's the axillary artery, the brachial artery, the profunda brachii artery. At the elbow, the radial artery and the ulnar artery. Now the nerves. Here's the musculocutaneous nerve, the median nerve, the ulnar nerve, and the radial nerve, with its superficial branch and its deep branch. That brings us to the end of this section. In the next section, we'll move on to look at what the upper extremity is all about, the hand. To understand the hand, we'll begin by looking at the bones and joints. Then we'll look at some important pulleys, and then we'll see the muscles. After that, we'll add the vessels and nerves, and lastly, we'll look at the skin. The terms that we'll use for orientation are ulnar and radial for the sides of the hand, radial being the side with the thumb, and palmar and dorsal for the front and the back. To begin looking at the bones and joints of the hand, let's see what they're called. Here are the 8 carpal bones, and here are the 5 metacarpals. Each finger has a proximal phalanx, a middle phalanx, and a distal phalanx. The thumb just has 2 phalanges, a proximal phalanx and a distal phalanx. The joints of the hand have long names. The joints between the carpus and the metacarpals are the carpo-metacarpal joints. The joints between the metacarpals and the proximal phalanges are the metacarpophalangeal joints. The joints between the phalanges are the interphalangeal joints, proximal and distal. We'll often refer to these joints as CMC joints, MP joints, and IP joints for short. To look in some detail at the bones and joints of the hand, we'll look first at the carpus, then at the 4 fingers with their metacarpals, then at the thumb with its metacarpal. We saw the individual names of the carpal bones in the previous section. Let's look at their overall shape. There are 2 bony projections on each side. On the ulnar side, the pisiform bone, and this part of the hamate, called the hook. On the radial side, the tubercle of the scaphoid, and the crest of the trapezium. With these projections, the bones of the carpus form the base and the side walls of a space called the carpal tunnel. Here's how the carpus looks in the living body. The radiocarpal and midcarpal joints are hidden by the heavy capsular ligaments. Here are those 4 projections again, the tubercle of the scaphoid, the crest of the trapezium, the pisiform, and the hook of the hamate. And here's the carpal tunnel, still without its roof. Now let's move on to look at the metacarpals of the 4 fingers and at their CMC joints. Here are the carpo-metacarpal joints. The bases of the 4 finger metacarpals, tightly packed together, articulate here with the distal row of carpal bones. The base of the first metacarpal, the one for the thumb, articulates separately here with the trapezium. These 4 carpo-metacarpal joints only allow a small amount of movement. The 5th metacarpal is the most mobile, the 4th is less so, the third hardly moves at all, and neither does the second. When the CMC joints are flexed, the metacarpal heads lie in a curve. This strong ligament is the deep transverse metacarpal ligament. It keeps the metacarpal heads of the four fingers from spreading apart. As it crosses each MP joint, the ligament is continuous with a structure that we'll meet shortly, the palmar plate. Since it doesn't connect to the first metacarpal, the ligament doesn't prevent movement of the thumb away from the hand. Next, we'll move on to the bones and joints of the fingers themselves. The proximal and middle phalanges are flattened on their flexor aspects. The flexor tendons run along here. The sheath that surrounds the flexor tendons is attached to these ridges. The tip of the distal phalanx is flattened. The fibrous pulp of the fingertip is attached here. The bed of the fingernail is attached here. Now let's look at the metacarpophalangeal joint, the MP joint. It's the joint at which the finger becomes separate from the hand. We'll take the other fingers away so that we can see it from all sides. The articular surface of the metacarpal head is curved in two planes, from side to side and from front to back. The base of the proximal phalanx has a concave articular surface that's also curved in two planes. The shape of the bones allows a wide range of flexion and extension at the MP joints. It also allows a range of side-to-side movement that's greater when the joints are extended, less when they're flexed. We'll see why that is in a minute. Let's see what the joint looks like in the living body. The MP joint has a capsule that's loose on the back to allow the joint to flex. On the front, the capsule thickens remarkably into a tough piece of fibrocartilage, the palmar plate, also called the palmar ligament. The palmar plate moves along with the proximal phalanx when the joint flexes. Here's the palmar plate incised to show how thick it is. As we'll see, some important structures are attached to the palmar plate, or merge with it. One of them we've seen already, the deep transverse metacarpal ligament. It goes here. Here, we've removed most of the joint capsule so that we can see the two massive collateral ligaments which hold the MP joint together. The collateral ligaments run obliquely from the back of the metacarpal head to the front of the base of the proximal phalanx. The collateral ligaments are loose when the joint is extended, but when it's flexed, they become tight. So when the joint is extended, side-to-side movement can occur readily, but when the joint is flexed, the tightness of the ligaments prevents side-to-side movement. We need to understand the names that are given to those side-to-side movements at the MP joints. Spreading all the fingers apart is called abduction. Bringing them all together is adduction. Those are useful terms for describing those collective movements of the fingers. But when we're speaking of an individual finger, it's often simpler to speak instead of ulnar deviation and radial deviation. Now let's move on to the interphalangeal joints. The proximal and distal IP joints are very much alike. They're different from the MP joints in that they only allow flexion and extension. The head of the phalanx is curved mainly from front to back, with a slight depression in the middle. The base of the adjoining phalanx has a corresponding curve to it. The capsule of an IP joint is much like that of an MP joint. But the collateral ligaments are different, in that they're equally tight in flexion and in extension. Now let's move on from the fingers to look at the bones and joints of the thumb. The first carpometacarpal joint is the joint which gives the thumb its special position and a great deal of its special mobility. Let's take off the metacarpal heads to see the joint surfaces. Here's the first CMC joint. It sits in front of these other CMC joints and at an angle to them. Because of this, the thumb and its metacarpal lie in front of the fingers and their metacarpals. Because of the angle of the carpometacarpal joint, the thumb faces not forward as the fingers do, but sideways across the hand. The articular surface on the trapezium is curved in two planes, from side to side and from back to front. The base of the first metacarpal is curved in the same way. The shape of the joint surfaces enables the first metacarpal to move in this plane and in this plane. We'll name those movements in a minute, but first let's look briefly at the other two joints of the thumb. The MP joint of the thumb is unlike the finger MP joints. It's much more like an interphalangeal joint. It permits only flexion and extension. On its flexor aspect there are two tiny sesamoid bones, which are embedded in the joint capsule. The one interphalangeal joint of the thumb is just like the IP joints of the fingers. Now, let's go back to the CMC joint and see how the first metacarpal moves and what the movements are called. Movement away from the second metacarpal is called abduction. Movement toward it is adduction. Movements at right angles to this axis are called flexion and extension. These two sets of movements often happen in combination. As it makes these movements, the first metacarpal also rotates around its own long axis, as the pen is doing. When it's abducted and flexed, it rotates medially. When it's adducted and extended, it rotates laterally. This rotation can't happen in isolation, but only as part of those other bigger movements. It happens because of the curious and complex shape of the CMC joint surfaces. This important and complex movement of the thumb is called opposition. It's a combination of abduction, flexion, and medial rotation, all occurring here at the CMC joint. Because of the rotation that occurs, the tip of the thumb ends up pointing toward the fingers. Once the thumb is in opposition, flexion at the MP and IP joints brings the tip of the thumb into contact with the fingers. We've looked at the bones and joints of the hand and at the movements they're capable of. Before we move on to look at the muscles which move the fingers and thumb and the tendons by which they act, there are a number of important pulleys and sliding structures that we need to understand. These structures guide the direction of pull of the tendons as they cross the wrist joint and pass along the fingers. We'll look first at the two big pulleys at the wrist, the flexor retinaculum and the extensor retinaculum. Here's the flexor retinaculum. It's a tough, unyielding strap of fibrous tissue. The flexor retinaculum is the structure that forms the roof of the carpal tunnel. It's attached on the radial side to the scaphoid and the trapezium, and on the ulnar side to the pisiform bone and the hook of the hamate. As we'll see, the median nerve and all the flexor tendons to the fingers and thumb go through the carpal tunnel. The flexor retinaculum branches off in two places, here and here, to enclose two small separate tunnels. This one, on the radial side, encloses the tendon of flexor carpi radialis. This one, superficial and on the ulnar side, encloses the ulnar artery and nerve. We'll be returning to the flexor retinaculum later to look at some important structures that arise from it, the palmar aponeurosis and some of the thenar and hypothenar muscles. Let's go round now to the dorsal aspect of the wrist to see the other big pulley, the extensor retinaculum. It runs obliquely from this ridge on the radius to the ulnar styloid, the triquetrum, and the hamate. The extensor retinaculum has a number of deep extensions which are attached to the underlying radius. These divide the space under the retinaculum into several small separate tunnels. All three wrist extensors and all the extensor tendons to the fingers and thumb pass under the extensor retinaculum. Now let's look at the structures in the fingers and in the thumb which hold the flexor and extensor tendons in place, allow them to move, and guide their direction of pull. In each finger, this structure, the flexor tendon sheath, provides the two flexor tendons with a smoothly lined, tightly enclosing tunnel to run in. The sheath starts just proximal to the MP joint and extends all the way to the distal phalanx. To see the sheath better, we'll divide it. Parts of the sheath are thick and fibrous, and parts of it are thin and collapsible. On this finger, we'll remove the thin parts of the sheath and just leave the thick parts. These act as pulleys for the flexor tendons, as we'll see. At each joint, the sheath is attached to the edge of the palmar plate. Between the joints, the sheath is attached along each phalanx. The floor of the tunnel for the flexor tendons is formed by the palmar plates and by the smooth, flattened surfaces of the phalanges. The thumb has a similar flexor tendon sheath for its one long flexor tendon. The arrangement for the extensor tendon is entirely different and quite complex. On each finger, the extensor tendon and the tendons of three intrinsic muscles come together to form a structure called the extensor mechanism. Let's take a look at it. We'll look at the muscles themselves a little later. So that we can see the extensor mechanism from all sides, we'll look at one finger in isolation. Here's the extensor tendon approaching the back of the MP joint. Here, both on the radial side and on the ulnar side, is the tendon of one of the interosseous muscles. In addition, here, on the radial side only, is the tendon of a lumbrical muscle. On each side, a triangular sheet of tendinous tissue fans out and connects the extensor tendon to the interosseous tendon. This triangular sheet is called the extensor hood. The big extensor tendon divides into three slips over the proximal phalanx. The central slip crosses the proximal IP joint and inserts here, on the base of the middle phalanx. The slips on each side fuse with the interosseous tendon to form the two lateral bands. The lateral bands join together over the middle phalanx and insert here, on the base of the distal phalanx. The thumb doesn't have such a complex extensor mechanism. The insertion of its two extensor tendons is relatively simple, as we'll see. One last structure to look at before we move on to muscles is the palmar fascia, or palmar aponeurosis. It's a dense triangular sheet of fibrous tissue which covers the middle part of the palm of the hand. Proximally, it's continuous with the flexor retinaculum and with the tendon of palmaris longus. Distally, it separates into slips which insert into the edges of the palmar plates of the MP joints. The palmar fascia protects the underlying nerves, tendons, and vessels from harm. The skin of the palm of the hand is firmly attached to it.